Welcome to String Theory, the story of everything. The story of string theory is the story of a theory that aims to explain everything from neutrons to universes to gravity in one unified set of equations. Our story begins with gravity. Einstein's theory of general relativity predicts a smooth, classical universe. However, quantum mechanics rocked this conventional notion of physics with its chaotic, jittery space-time landscape. Comparing quantum mechanics and general relativity, two equations both describing the laws of nature, results in crazy mathematical inconsistencies. These two theories both aim to describe the nature of the same universe, yet they're incompatible. This is where string theory comes into the picture. String theory unifies these two mutually exclusive theories by giving particles dimension, thus creating a minimum meaningful length known as the Planck length, a distance so small that were an atom expanded to the size of a solar system, the Planck length would be the size of a tree on Earth. Having a minimum non-infinitesimal space changes the behavior of general relativity on small scales and avoids the chaotic space-time that quantum mechanics predicts to exist on smaller levels. String theory did not always have this purpose, though. Strings were first used in the late 1960s when it was realized that certain formulas made sense when describing the strong force if the particles involved were viewed as strings. However, such a theory was shown to exist outside of quantum mechanics, and a better theory was developed to explain the strong force. This led to all but a handful of physicists to forego their research in the field. Those who remained shifted their attention to quantum gravity. They realized that if gravity were quantized to gravitons, those gravitons would have the properties of a particle that string theory predicts to exist. In this sense, string theory predicts gravity. The original true incarnation of string theory was known as bosonic string theory, which applied only to bosons. Bosons are particles such as photons and gravitons that carry a force. The theory did not, however, apply to fermions, the particles between which bosons are transmitted. Bosonic string theory also predicted the existence of tachyons, which are particles with imaginary mass that travel faster than light. Both of these were problematic for a true theory of everything. A different oddity of bosonic string theory was that it necessitated the existence of 26 spacetime dimensions. While 26 spacetime dimensions may seem outlandish merely because we only observe 4, it is quite possible that our universe contains more dimensions than meet the eye. In fact, the subsequent version of string theory predicted 10 spacetime dimensions. The extra 6 dimensions predicted by that string theory must be folded very tightly into geometric structures known as Calabi-Yau manifolds. Calabi-Yau manifolds are multidimensional curls on the scale of a Planck length or larger. Fermions were also included in that iteration of string theory due to the idea of supersymmetry, which is the idea that every fundamental fermion has a corresponding supersymmetric boson, playfully known as a spermion, and every boson has a corresponding supersymmetric fermionic partner. Certainly a theory explaining anything in the universe should be unique. However, for a time, there were 5 independent forms of string theory that were all equally valid. Eventually, in 1995, Edward Witten introduced M-theory, which fixed this problem by adding another dimension to string theory, showing that the 5 competing forms of string theory were actually different islands that existed on the same planet. Any worthwhile scientific theory should be testable. This is unfortunately where string theory encounters problems. Any mode of direct detection of strings would require technology that will not exist for hundreds or even thousands of years. There may be indirect methods to test for string theory, though. The LHC provides the best hope we currently have of testing string theory, and this could be accomplished by attempting to observe supersymmetric particles, or by observing events that would indicate extra dimensions are involved. All in all, there are very few experiments that could either support or refute string theory in the foreseeable future. Even without potential experiments, String theory continues to captivate physicists with its beauty and elegance in unifying general relativity and quantum mechanics, two previously incompatible theories, into one harmonious theory of the universe. And this is where our story ends. But string theory is just in its infancy. Who knows how many more colorful chapters lie unwritten in the story of everything.